We're currently looking deeply into the different biomes of our planet and what the characteristics of each are. But I want to take a moment to remind us of why these biomes exist where they are and what their connection is with our global climate. So we talked a little bit about the climate of our Earth and the different global processes that determine what climate exists where. So remember that weather is very short-term conditions. They're very localized, so humidity, cloud cover, wind speed, those have to do with weather. Climate is a more long-term average of what occurs over a long period, typically up to several decades. For instance, is it hot in Texas? Well, it might not be hot today, but typically it'll be warmer in Texas than it will be in Minnesota. That's more of a climate, a longer expectation of what conditions will be like. Our temperature and precipitation patterns usually come from a couple different sources. One is the sun's energy and how that energy falls differently in different places. Those convection currents that we talked about in the atmosphere, how the Earth rotates, which affects the direction of the wind as it moves across the surface, how our Earth orbits around the sun and how that axis is tilt, which gives us the different seasons, and then the ocean currents that cycle through the globe. Those can all determine what temperature and precipitation appears in different places. Our atmosphere, which determines the weather, is that troposphere. That troposphere is what gives us our weather conditions. The stratosphere, however, also plays a part. That stratosphere is the location of our ozone layer, which can trap heat. And we do have some weather clouds. Some of the big clouds can reach into the bottom pieces of our stratosphere there. So the sun hits the Earth's surface differently. And then, of course, when the Earth absorbs that heat, it absorbs it in different ways depending on the albedo. So in addition to hitting the equator more directly and the poles more indirectly, we also, once that sunlight hits the Earth, the different surfaces will absorb it different ways. The ice will almost completely reflect the sun's radiation. Asphalt will almost completely absorb the radiation and turn hot. So I'd rather run across a grassland where a lot of that energy is reflected back than run across asphalt where all that energy is absorbed. So the albedo, we talked very briefly about. Albedo is the reflectivity, the amount of sunlight that's reflected back off of a surface. Now, the air itself has different properties that determine how it moves and how it cycles energy. One is density. When air is less dense, it rises. When it's more dense, it sinks. Water vapor capacity. The water vapor capacity is higher in warm air. It can hold on to more moisture than cold air. That's why your equatorial regions where it's very warm tend to be very tropical, very wet, while your polar regions where it's very cold tend to be more dry. There's a heating and cooling process called adiabatic heating and cooling, and that has to do with pressure. So think back to chemistry with your gas laws. As that pressure decreases, your air expands and it also cools. As air sinks, the pressure increases and it warms up. And then finally, latent heat release. When water vapor condenses into liquid, such as forming clouds, that energy is released. So when water condenses, the air warms and then it will rise. We get a lift with our cloud cover and that leads to more precipitation. Here's our convection currents. We've already discussed those Hadley currents, the polar currents, the Hadley cells, the polar cells. And then one thing that we didn't discuss earlier is an area called the Intertropical Convergence Zone, the ITCZ. That's that area along the tropics where that moist air comes together and rises and then it rains. So this is your tropical area at the converse, the coming together of two Hadley cells there. All right, also as the Earth rotates, we get a little bit of that Coriolis effect that we've talked about. Here's just a reminder there. As it rotates, the surface goes a lot faster at the middle than it does at the poles. It's just kind of barely wiggling at the poles. And so that faster rotation at the equator causes your winds and your currents to deflect along those Coriolis lines there. Okay, so there's our prevailing winds. We talked a little bit about the trade winds and the westerlies and those polar cells, all having to do with that spinning of the Coriolis effect. Of course, remember we talked about the seasons and how Earth is tilted. So our incoming solar radiation will be different at different parts of the year, depending on whether we're pointed towards or away from the sun. And our ocean currents can also play a big part in the local temperature and precipitation. Our ocean currents, just like air, whenever it's warm, will expand and rise, and whenever it's cold, will become more dense and sink. Where we get big patterns of water circulation, we have what's called gyres. So gyres or gyres, however you want to say it, it's almost like a water tornado, except not that tight. It's a much bigger circulation. But where you get that, you get a circulating current. You can see a couple of them here on our map, these gyres that are spinning there. So these are your warm currents. You can see the Gulf Stream coming right up here along the North American East Coast. And the current there will zip all the way across the North Atlantic and deposit that warmth up here in Northern Europe. So if you notice, remember Spain is real nice and warm and tropical, and you can go to the beaches in Spain. If you look directly across the latitude line, you're in northern United States, Maine, Canada, not very tropical and warm. The reason for that is the cool air coming down and making this area colder, and the warm water going across and making this area warmer than it normally is. And all this has to do with, just like the air currents, it has to do with warm rising and heading north, cooler sinking and heading south. Where you get those surface currents separating from one another, the deeper waters rise to replace that. And where the deep waters come up to replace the water that's moving away, you get what's called an upwelling. And with that upwelling, it brings nutrients from down in the ocean bottoms that support large amounts of plant producers. And then the plants, the producers, support large amounts of fish. So you do tend to get big schools of fish, big communities there where you've got upwelling currents from the surface water moving out of the way and the deep waters coming up to replace it. There is circulation patterns that don't have to do with temperature. They have more to do with the haline, the salt concentration. So our thermohaline circulation is a circulation, a mixing of our surface water and our deep water that have different amounts of salinity and thus different densities. If it has more salt in it, then it's more dense. If it has less salt in it, then it's less dense. And this haline circulation actually circulates nutrients as well around the globe. Next, there we go. So here's an idea of that thermohaline circulation going all the way around the world, those ocean currents. Okay, so we can take that heat and transport it from one area to another. So here's that example we were just talking about. England's average winter temperature is approximately 20 degrees, which is 36 Fahrenheit. Warmer than it is in Canada, which is at that same latitude, and it has to do with that ocean current bringing the heat with it. We talked a little bit in our last section about El Nino when we were talking about our hydrosphere. Every 3 to 7 years, those waters will kind of slosh back and forth and bring the warm, wet weather with El Nino to North America, South America, and then it'll slosh back the other way, and it'll be cold and dry in North America and warm and wet over in Australia. So it's kind of a sloshing back and forth over 3 to 7 years. Okay, so it has to do with the winds weakening, that equatorial water sloshes one direction, upwells, and then back the other way. So with that sloshing, we actually also get an upwelling event, which it suppresses the upwelling. Sorry, I'm thinking backwards. And so we don't get the upwelling that we normally get, and our fish populations off the coast of South America don't do as well because we've suppressed that normal upwelling. Then when it sloshes back, then the opposite will happen. We'll have more upwelling and better fish populations off of South America. Okay. We talked very briefly about rain shadows. Rain shadows have to do with that adiabatic cooling that we talked about when the weather is coming off the ocean, whenever it gets to a mountain range. So think like Washington State and the Cascades. When the wet, warm water is coming off of the Pacific Ocean, it hits that mountain range, those Cascades, and tries to go over it. As it rises over the mountain, it rises, it's less dense, it cools, and it loses that moisture. So that precipitation falls on the western side of the Cascades, and then the air that makes it over ends up being drier and colder on the other side. So we get more arid conditions on the other side. So here's that picture of our rain shadow. Moist precipitation on one side, and then arid conditions on the other. Okay, so all this climate, the reason that I'm pulling this back out and talking about it yet again, even though we've covered that and had our test, we're pulling it out and talking about it again. The reason is because that climate determines what plants can grow there. The upwelling and the saline conditions determine what can grow in our oceans. So that climate, those conditions determine where our plants are, which determine where our animals are, which determines what biome we're in. The organisms tend to be adapted to a particular temperature and precipitation pattern. So those biomes tend to have similar plants no matter where they're at on the globe because they have similar temperature and precipitation patterns. So we can divide biomes into 5 major types, and then of course with you guys I divided them even further, but we've got major types of like desert-like conditions, of course our aquatic biomes, forested areas. Now you can have deciduous, or you can have conifers, you can have temperate, you can have tropical, but you have areas where there's lots of trees. There's grasslands, and then of course our tundra areas. The thing that really determines what biome exists there is the temperature and precipitation. Now we're talking terrestrial. For aquatic, it would be the depth and the salinity. And our biomes, if you look at a map, they tend to be on certain latitude lines because that's where you tend to find those temperature variations. So now that we've looked at why biomes exist where they are, we're going to dig, of course, deeper into what specifically our biomes are like.